Alright, welcome back everybody. In this video we're going to look at examples 4 to 6 from the Lengths of Curves lesson. So we'll start with example 4, and this comes directly after a little bit of narrative about finding the length of a curve with a corner or cusp. And this equation is one where if we look at the graph of it, we'll see that the curve indeed has a corner or cusp on its graph. Let's take a look at the graph first, so we can see what's going on. So I'm going to go ahead and graph y equals x squared minus 4 absolute value of x minus x. And check out my window. Okay, standard window. And we see there's a cusp point here at x equals 0. And so what we're going to end up doing is we're going to end up splitting this curve at x equals 0 in order to find the arc length from -4 to 0 and then the arc length from 0 to 4. So what we need to do is we need to find the derivative of this function for both pieces on the cusp point. And the way we're going to do that is we're going to define this function in a piecewise fashion. We're going to say that y is equal to, and where the cusp occurs is at x equals 0, and that's because of the absolute value, because the absolute value turns negative values positive, and that's what leads to the hard corner there. So when we define this piecewise, we're considering what happens when x is greater than 0 and what happens when x is less than 0. And what happens when x is greater than 0, greater than or equal to 0, pardon me, what happens when x is greater than or equal to 0 is the absolute value leaves what's inside those bars unchanged. And so this function is x squared minus 5x for x values greater than or equal to 0. Then when x is negative, the absolute value takes the opposite of that. So this simplifies into x squared minus 4 times the opposite of x minus x, which means that the function is equal to x squared plus 3x for x values less than 0. So we have this piecewise defined function, and we're going to have two separate derivatives and two separate integrals to find the length of this curve. So first I'm going to find the derivative. dy dx is equal to 2x minus 5 for x values greater than or equal to 0. And it's equal to 2x plus 3 for x values less than 0. And this is good for us because since our cusp point is at 0, we're going to split this into two integrals. One integral that runs for the arc length from -4 to 0, and the other one that runs for the arc length from 0 to 4. And then we're going to add those two arc lengths together. Okay, so my integrand for the first is going to be my bottom piece of my piecewise function. And we'll just take 1 plus dy dx quantity squared with respect to x. And then we'll do the same thing with the other piece, square root of 1 plus dy dx quantity squared. And now I'm going to calculate the value of this total arc length by using two separate integrals. So we'll take our integral of the square root of 1 plus quantity 2x plus 3 quantity squared, goes to square root, from -4 to 0, and we'll add to that the integral of the square root of 1 plus quantity 2x minus 5 quantity squared with respect to x from 0 to 4. Hopefully I didn't forget any parentheses or anything in there. And this will calculate for me the total arc length overcoming the fact that there is a cusp at that point. And what did we get? 19.556 for our arc length. Okay, that's example 4. Looking at example 5. Find the length of the curve x equals the integral from 0 to y of the square root of secant squared minus 1, from y equals negative pi over 3 to y equals pi over 4. Alright, so this is an unusually defined function for us. We're defining x as an integral of a function instead of as a function itself. But this is actually going to make things fairly easy for us. When we go to find dx dy in order to use it in our arc length formula, all we're doing is taking the derivative with respect to y of the integral from 0 to y, and it looks like I'm missing a t in there, yeah I am, of the square root of secant squared of t minus 1 dt. Now this derivative, because of the fundamental theorem of calculus, is just going to be square root of secant squared of y minus 1. And so that's what's going to go into our arc length formula. Our arc length formula is going to turn into the integral from negative pi over 3 to pi over 4, pardon me, of the square root of 1 plus dy dx squared. And dy dx squared, we just square that square root. And so this is going to be the secant squared of y minus 1. And so really, all this turns into is it turns into the integral from negative pi over 3 to pi over 4 of, and if you simplify all this, the 1's cancel, 1 and minus 1 cancel each other out. The square root of secant squared of y is just secant of y dy. And so at this point in time, I could opt to integrate this by hand, which I'd prefer not to, but we certainly could. And you guys hopefully remember how to integrate secant of y. Or we have the option again to calculate this numerically. We're going to take the integral of 1 over cosine of y with respect to negative pi over 3 to pi over 4. And that works out just fine for us. We find the length to be 2.198. We would have potentially been in some problems if the any point in the interval negative pi over 3 to pi over 4 had a cosine value that was 0, but thankfully our limits of integration were cooperative and we didn't have that in this case. Alright, example 6, kicking it old school. We're going to find the exact length of this curve from x equals negative 2 to x equals 1, and we're going to do it algebraically by using anti-differentiation. Now back in my day, when I took AP Calculus, we didn't have graphing calculators that we could use to find the integrals of these values. And that really limited the number of problems that we could do finding arc length, because in order for us to find the arc length, we had to be able to have an integral where after we simplified it, it was something that we could take by hand. And this is one of those problems, one of those few in that handful of problems that we could use. First we find dy dx using the fundamental theorem of calculus. We get that dy dx is equal to the square root of 3x to the 4th minus 1. And then we'll set up our arc length integral. It's going to be the integral from negative 2 to 1 of the square root of 1 plus dy dx, the quantity squared, with respect to x. Simplifying this, the square of the square root is just what's inside the square root. And this turns into the integral from negative 2 to 1 of the square root of 3x to the 4th dx. and I take the square root of 3x to the fourth, and that's the square root of 3 times x squared. I'm going to bring the constant square root of 3 out in front of my integrand. And now I can just go ahead and integrate this by hand. It's going to be x to the third over 3, evaluated from negative 2 to 1. And so this becomes square root of 3 times 1 to the third over 3, which is 1/3, minus negative 2 to the third over 3. And so that all turns into square root of 3 times 9/3, or 3 square root of 3. And there's the exact arc length of that curve using a little bit of algebraic manipulation. Alright, that's the end of this video and the end of the lesson on finding arc lengths. See you guys next time. Have a great rest of your day.